since we've been talking so heavily about Unicode, I want to go back a little bit to ASCII. So let me make sure my pencil is big enough here. And let's draw kind of a box. It doesn't seem like it's big enough. And a second box. And let's assume these are electronic devices of some kind. They could be computers. They could be different parts of a system. It could be circuit boards in a system. They could be individual chips on a particular circuit board. But for whatever
Professor,
reason...
sorry to interrupt, but we can't see anything.
Okay.
You're not sharing anything.
Okay.
Yeah.
I can't see that screen, so thank you for telling me. This has been kind of a strange lecture if I didn't give you a picture to look at. I think it's this one. Yeah, mine says I'm already sharing, but I think I have to hit that button also. There we go. You got two boxes up there. That's all you've missed.
Yes.
Okay. Now, these two pieces could be computers. So this could be computer A, this could be computer B, and it has a need to communicate with the other box. This could be a circuit board. Has a bunch of chips on it, but the board itself has some function where it needs to talk to a different circuit board in the system. This could be a CPU, this could be a North Bridge, for example. These two chips might be able to talk to each other. So we know minimally there's got to be some sort of a wire of some sort. Even if we're talking radio here, eventually we're going to hit a point where a wire is going to magically appear. And we can think of these guys connected in a way. Perhaps the communication can only go from box A to box B. That's just fine. We could imagine a wire which could do that. And we could say that we expect box A, when some particular event that's interesting occurs, to pass that event to box B by simply maybe signaling on this wire. Maybe it is normally sitting at 0 volts, it raises it to 5 volts, and then perhaps lowers it again. And that little signal tells B that some event has occurred. Well, as you start to get lots and lots of events and states and signals you need to pass, this could become very large. Maybe this is, 100 individual wires that have to go between point A and point B. And we call that type of communication parallel. Now, one of the advantages to it is that in parallel communications, things happen all at the same time. So these 100 events would be seen by B at the same moment, perhaps. However, that's a lot of wiring, and could be, particularly in long distance, let's say this is in one building and this is in another building, and these have to talk, there would be 100 wires running between them if we didn't use some sort of networking to, limit it. But minimally, there'd be 100 wires running to something that then networked it and would resume the 100 wires on this end. So let's forget about networking, just say we got 100 wires. Parallel, while fast, is probably not necessarily a really good solution all the time for communicating. Sometimes it is. Old disk drives used to communicate in a parallel fashion with their controller boards. Modern times, though, we might consider, let's use a single wire, but let's send the data as a stream of bits. So we're going to send the stream of data, ones and zeros, as a stream of bits rather than sending it in parallel. This type of communication is called serial. Now, this is not, Captain Crunch, but it's serial, like one after the other. Our ducks are in a row. And in a serial communication, we're going to send a bit, send another bit, send another bit, send another bit. There's two main types of serial communications. One is called synchronous. I'm just going to write sync. And the other is called asynchronous. I'll just write async. Synchronous communication says there is minimally 2 wires in the system. One of the wires is sending data, and the other wire is being used as what we'll call a clock. I'll abbreviate it CLK. Now, the idea is that every time we want B to read the data, we're going to take the clock perhaps from low to high and back again. B knows that while the clock goes high, it's safe to read the data. Then when the clock goes low, it waits and waits until it sees another clock, and then the next bit is changed by A, and then it can look at it. So there's a synchronization, that's what this would be for, between the data on two ends and some sort of clock that will cause the data to be read by the receiver. So we have a transmitter and a receiver and a clock signal. Now, a simpler way to do this, although this is very reliable, and in many protocols, particularly on small boards, you're going to see there are a couple protocols that will be used. One is a protocol called SPI, S-P-I, the Synchronous Peripheral Interface, and another is I2C, which is a communication protocol which is used, again, with a clock to send data in serial form. And we'll see these later in the semester and talk about them extensively. For now, just file them away in your head as something that you're going to see later. If we don't have the clock, however, and we only send the data, how would B know when it's supposed to read the data? Well, we have to build a contract between us and them that says we need to know what the bit rate is. How fast is the data being sent? Secondly, we have to agree on how many bits of data are there. So the number of bits of data. Are we sending 7 bits? Are we sending 8 bits? Are we sending 9 bits? How many bits of data are we actually sending in a transmission so we know when we have received a complete unit of bits? The last thing we might need to know, well, a couple more things. One is there any kind of parity? We talked about parity in the last class. And if there is parity, is it none? Is it mark? Is it space? Is it even? Is it odd? What type of parity is being sent so we can perhaps, if it's even or odd, do some sort of error checking and reject the message if the parity is wrong. And finally, we need to know the number of stop bits. At the end of the transmission of a character, we're going to put in some stop bits to say you've seen all the characters and possibly the parity, but I don't want to start sending anything else yet. This will force me to cause a little bit of delay to occur, so you may process the message before any other thing can happen. This will normally be either 1 or 2. Won't be long, but it'll be an amount of time when you can process the data that I am sending. So we've got to agree on a bit rate. We've got to agree on how many bits are in the data. We've got to agree on the parity, where the parity might be none, it might be mark, it might be space, it might be even, it might be odd. And you can just spell those words out. Number of bits of data are likely to be 7, 8, or 9. And the bit rate is going to be something we agree on because that's the speed at which I'm going to transmit it. And you have to be able to receive the data and then in the gap of time between characters, be able to react to any character you receive that requires an action. Of minimum speed we might see today is something like 1200 bits per second. You might hear that, if you talk to an old fogey like me, you might hear that called 1200 baud, B-A-U-D. Now, formally baud and bits per second are actually something different. And if we have a need to later in the semester, I'll talk about what the difference is. But casually, you might hear it called by that, particularly with people that were around when slower speed communication was more common. A very common speed you will see is the speed of 9600 BPS, bits per second. For small length messages, this will cause a message to be sent rather quickly. you know, obviously quicker than this, about 4 times as quick or more, you know. Actually it's more than that, isn't it? 8 times perhaps, close to. And the bit rate here is very common for small systems. So if you were to go get a job somewhere working on something that has to do with home automation today, very likely internally in the device, it may be talking between chips and boards and things at a much slower speed than you might imagine. And 9600 baud is a very often chosen speed. As we get into the AT Mega 328P chip, we'll use that with our computer at that baud rate, or bits per second. The speeds actually increase, and probably the maximum speed for serial communications you would run into for simple asynchronous serial communications is going to be 115,200 bits per second. We may do some experimenting with that later in the semester when we're using our processor to communicate. Obviously, higher speeds, bigger chance you're going to have an error. Remember, with parity, the best we can do is detect an error. We can't correct it. But with multiple bits of error, we can't even find those and see that they happen. So sometimes we have to use other techniques to determine, maybe we embed some data in the data itself, which will help us decode whether a message was sent correctly or not. The device we would use in order to send characters of this form is called either a UART or a USART. And for our purposes, they're fairly much the same thing. A universal asynchronous receiver transmitter. That means it can receive and transmit, meaning on both ends you could have a UART talking, one UART talks to the other one, and then the CPU, for example, would talk to the UART. Basically, the CPU would give the UART an instruction to send something. It would send it, and when it was done, it would notify the CPU that it was done. Or it might notify you that it has received a character. The USART means Universal Synchronous Asynchronous Receiver Transmitter, meaning it can also do things like this. It can do clocked protocols as well. We're mostly concerned with asynchronous here because the communications we've talked about here would allow us to send data in an asynchronous way. Now, the UART can be much, much faster than we would suspect. Let's assume I'm going to just draw some time and pretend like this little square wave I'm drawing here is being sent. And we have agreed that this is time going this way. This is time. This is voltage going up and down. So this is 0 volts at the bottom and perhaps, 5 volts at the top. And let's assume that each of these represent a bit. Well, when we get ready to sample the bit, we don't want to sample on a rising edge or a falling edge because we would be unsure about what we were seeing. We want to actually sample the data right in the middle of that time period. Sample again, right in the middle. Sample in the middle, and so forth. So when we have agreed on a time, what we're going to do is we're going to look for a particular edge. And once we see it, we're going to wait a certain amount of time before we sample. And that amount of time is going to be 1 bit unit plus a half. Then from that point on, we can check a bit unit distance in the future. We can see whether we think we're looking at a 0 or a 1. Now, because noise tends to happen in little bursts, generally most good UARTs don't look one time. At this halfway point right here, they really sample maybe as many as 5 times. They say, okay, I got a 0, I got a 0, oops, I got a 1, I got a 0, I got a 0. Then what they do is they take and they say, well, I got 4 zeros and I got 1 1. What I sampled must have been a 0. So if the number I see is 3 or more, I will vote for that particular bit to say that that's what I think I got, even though I might get 1 or 2 bits that are wrong. Now, the higher the number, the stronger chance it really was a 0 or a 1. Now, really cheap UARTs don't have that facility. They simply look halfway through. Whatever it is, that's what they report. but smarter ones will sample multiple times at that point and at a very fast rate and determine whether or not maybe an accidental bit has been flipped. And then they'll report the majority of the bits that they saw. Now, how would we find out how long a bit takes to transmit at 1200 bits per second? Well, let's bring up our grocery store calculator. And let's say if 1 second were divided by 1200 units, we would be getting a sampling at 83 milliseconds. Yeah, I just turned the 4 here into this. What if I was doing 9600? Well, I could invert that or just 1 into it. Again, the same thing here. Every 104 units, I'm going to get something. Now, are they milli or micro? I'll let you figure out whether we went to 3 or 4 and whether I was leading you down the path there. But you should be able to figure out fairly straightforwardly how long a particular bit is by dividing it. So if I took, 1 and divided it by 115,200, oops, I'll just make it 20, be close enough. We would see now that we have, unfortunately, our calculator doesn't report in engineering. Yours might, in which case you want to make this a 3 or a 6. But we can manipulate the decimal point to determine how fast that value would be per bit. Now let's assume for a second that we had some bits to send. We have to determine now what is it we're going to send and how are we going to send it. So let's take a character and we'll pretend like we're sending ASCII right now. ASCII, I type 2 C's there. In ASCII, let's say we're going to send the letter capital J. What is the letter capital J in ASCII? Meanwhile, I'm going to get my screen clean again. Well, J is the 10th letter, so it's going to be a 4 followed by a 10, which is A. So it has a hexadecimal value of 4A. Let's write that down in binary. 4A. Notice I didn't write the first nibble bit here because this is really not part of the ASCII. It would be where a parity bit would go. Now, when I'm going to send characters using ASCII, the protocol you're most likely to run into is a protocol called RS-232. It specifies the electrical and the protocol for communicating between 2 devices using a simple serial protocol, an asynchronous protocol. Now, it allows us to make the decisions that we needed to make. For example, if we agree, for instance, we're going to send at 1200 bits per second, and we're going to send 7 data bits, we're going to send no parity bits, which is basically what? Parity none. And we're going to send 1 stop bit. The 2 ends can agree to follow that protocol. Now let's assume for a second that they were going to do this. Well, in order, if this had parity to compute it, remember the parity bit would be right here. So to compute it, we actually have to send the bits in that order. And we have to receive them in that order so that we know by the time we get here how to compute what the parity bit should be. Remember, we're receiving these bit in a serial order. We're not getting them all at once and then looking at the thing. We're just getting bit after bit after bit, and we have to know how to deal with that. So let me see if I have, and I think I do, maybe I haven't opened that up yet. Yeah, I have. Here's the RS-232 standard on a timing diagram. There's 2 different voltage level standards. The one at the bottom is used between devices that are not close to each other. The one at the top is used between circuit boards and between small devices and computers. We'll most of the time be interested in this one, but we pay lip service to this one. When this one is not sending any data, we would be on this front edge right here, and it holds minus 12 volts on the data line. So anytime we're not transmitting, before we start sending a message, we hold the data at negative 12 volts. Could be negative 15, could be negative 9. I mean, this voltage is variable, but it's symmetrical around this one. Now we call this a 1. Even though it's the low value, this is a 1. The high value is a 0 when we're using this particular voltage scheme. Let's us mostly pay attention to this one, however. This is what we would be using. 5 volts is used for a 1, and it's also called a mark. 0 volts, which is here, for example, is used for a space, and the 0 volts is also equal to the binary number 0. So the way we start a transmission is using a start bit. And a start bit is when we have been idling at 1, meaning we're not sending a character right now, and we see a transmission on the data line that drops to 0. For this period of time right here, we're asserting a start bit. So this start bit, I'm going to make it be ST instead of spelling out start for the moment. Now, start bit is always a 0 if we're idling on 1. Actually, it's always a 0 down here. It just happens to go from minus 12 up to plus 12 to do the start bit. But once we've seen a start bit, we're no longer idling. This is idle over here. But we're actually going to receive a character until we have received the appropriate number of stop bits that we agreed to. We agreed to 1 stop bit. Now I'm going to start sending the actual data. The letter J, let's write it down again over here, is 4A, right? So 4A is 0, 1, 0, 0, 8, I'm sorry, 1, 0, 1, 0. We said no parity, so we know we're not going to send that 0 with no parity. We might have parity in our example here, in which case we'll restore it. But we're going to send from this end this way. So we're going to send 0, 1, 0, 1, 0, 0, 1. 0, 1, 0, 1, 0, 0, 1. Actually, we did send parity here, which is this guy right here. We sent a 0, so we'll remember that for the moment and come back and talk about it in a second. And then we send a 1. This one is the stop bit. I'm just going to put SP for stop. The stop bit, when it's over, we re-enter the idle condition. Or if we had another piece of data to send, we would immediately assert a start bit, but it wouldn't happen until after the stop bit has been seen. Now, if there's a 0 here, which means we're sending 7 data bits plus 1 parity bit, what does the parity mean? Well, in the data itself, we have 1, 2, 3 ones. We did not add another one. So this could be either we have a odd parity, meaning we already have an odd number, so we send a 0. It could also be that we're sending space parity, meaning there's always send a 0 in this position. We don't know. Let's assume that the J was sent with odd parity, in which case there is no error. The receiver is going to receive. He's going to see the 0 happen. He's going to say, oh, here comes a character. He's going to wait from this edge 1 clock cycle plus a half and start looking at the data. Then he's going to look every clock distance. And how long does he wait? Well, if we're broadcasting our data at 1200 bits per second, it's going to be whatever the length of a 1200 bit is. He's going to keep looking at those spots to see what bit he got. The receiver, by the time he gets here, will have received all 7 bits he's expecting, and he will recompute himself the parity. 1, 1, 1, he says, oh, it's odd, I better receive a 0 next. He'll now receive the next character. It is a 0. He knows he had no error, so he can continue. Next thing he should see is a stop bit. He will wait now, and after the stop bit, look to see if there's another falling edge. We assume sometime out in the future, another start bit is asserted. He waits through it halfway and all the way into the next bit to do its next sampling. So this is the way the RS-232 transmission of a letter J would look if we were looking at it. Now we could change the protocol. We could say, let's send 8 bits with no parity, meaning this 8th bit could be set to anything we want. Could be 7-bit with even parity, in which case we would have seen a 1 here. Could be 8 bits with parity, meaning we're going to send a 9-bit piece of data. So there's all sorts of options here, but if you see, we have to be able to agree on what those 4 things were. Did I leave them still on my list over here? No, I got them arrayed, but what are the 4 things? The bit rate. We have to agree on the speed. We have to agree on the number of data bits. We have to agree on the number of stop bits. I'll just call it SP here, because T looks like start. And we have to agree on one other item, and that's the type of parity. I may have listed these in a different order. So parity, question mark, and if so, which type? But once we've agreed on that, and as long as we honor those conventions, we should be able reliably to send bits of data. So if I send a character to you, I've basically sent you 8 or 7, really 7 bits of entropy, which you can assume was better than me sending you in parallel 100 pieces of data later, because all I have to do is send you, what, close to 120 characters or something, and you will have seen the same amount of data. And as long as the asynchronous protocol is fast enough, then I don't have the problem of maintaining on a circuit board, 100 lines next to each other, which cause their own problems if we're building a circuit board. Very hard to route that many wires. Does anybody have any questions at this point? Okay, give me a green light if you could still hear me okay. Okay. I think the next topic we shall talk about tonight is going to be the IEEE 754 floating point standard. So let me clear some of this out of here in case I need this later. I'll select it and delete it. Oops, not with that key I want. Perhaps this one. There we go. And I'll put this down here. This guy we won't need again. Notepad we will need. Okay, we were really going heavy on Unicode, so you should be the masters of that by this point. But last time we had class, we talked about the notion of floating point, well, actually fixed point binary. If I give you a number, a decimal point, and then some other bits, you should be able to tell me what that number is. Now, the purpose for fixed point is it's much, much easier to do addition and subtraction if the points are over each other. And if you think about when you add and subtract numbers in decimal, you do that. You line up the decimal points, and then you have things to the left and things to the right, and you know what to do, and you can deal with a carry over the decimal point. So fixed point is rather easy, but it has very limited hardware support. Basically, we have to remember where this dot is because we're only going to be given this number and that number, and we're going to know that the decimal point stayed 4 positions over because that's the way adding and subtracting works. Now, if we multiply things together, that's not exactly the case. If I take 10 and I multiply it times 5, say times 5, I'm going to get 50, right? Well, the 10 looked like that and the 5 looked like that, so our decimal points being lined up didn't really help us determine where things were in the final number. So one of the things we want to worry about here is, can we get some sort of hardware support for the decimal point? And it turns out that indeed we can. In the processors of modern times, we have something called a floating point coprocessor. And that coprocessor uses the IEEE 754 floating point standard. Now there's lots of variations of this. We're going to specifically work on one called the single precision. We'll learn how to use that. And then all the others will just kind of fall into line for us, and they'll just make sense. But the idea now is that if I have a number and I want to either multiply or divide, could I please have some hardware support? And yes, indeed, the coprocessor will help us do that. It will keep track of where the decimal point is for us. Now, what does it mean to be a floating point number or even just a fixed point number? It kind of means I've got some numbers. Let's do it in decimal first of all. Let's say I had 123.2 or something like that. Each of these positions, this is times 10 squared, 10 to the first, 10 to the 0. And this is times 10 to the, minus thing, because we're going to flip it upside down and it's going to be some fractional thing at tenths. Next one would be 100ths and things like that. So ideally, what we'd like to be able to do is we'd like to be able to encode this number in some way where we could represent it times some power of 10, 10 raised to the n. We don't care what it is. But because we want it to maintain the decimal position for us, and we want it to be simple, what we'd really like to do is normalize this number. I would really like to have put 10.101 times 10 to something where the decimal point has been fudged, I'll use an m, so that it will recover the original number, but I can always specify my whole numbers as a single digit in front of the dot. That would be so convenient in terms I'm thinking about if I were designing the hardware for that. And I know more than you do about it, but you can intuitively think that that's got to be easier. If all our numbers look like they're in a standard place and all I have to do is maintain where the decimal goes, that's going to mean things are going to work like they're in fixed point, which is easy to write code to do adding and subtracting. But the net result will be that at the end, somebody can take it and they can expand it back to a number which might have many digits in front of the decimal point, or might have many zeros before the valid digits after a decimal point. So I want to kind of do this. This process is called normalizing, or normalization, or it's in normal form. But the idea is we're going to do that to our numbers. Now let's work in binary for a second. I'm going to take those numbers at the top, the 1010.1100, and say if I were to normalize that, what I really would like to do is take and put everything so it's like that. I'd like to get a single one to the left of the decimal point. That way, I never have to worry about what the magnitude of this number is, because I'm going to somewhere else keep track of the exponent I have to raise. Let's put a Q there. I have to raise 2 in order to get this back to be the original value that I was dealing with. And if I could also make sure my number, my final answer always comes up this way, everything can be consistent in the hardware in terms of dealing with it. So the second number, which is actually 0100.0011, to be normalized would look like that. And we would probably throw that 0 away because it's not important. So again, I can normalize this second number by simply sliding the decimal point over 3 places, well, 2 places in this case. In the other, I moved it over 3 places. So to get from here to here, this means this has to be multiplied times 2 to the third. This guy has to be multiplied times 2 squared. So there's a couple things in my number here which then become, I can just assume them. If I know all my numbers always start 1 point, I never have to encode that anywhere. I can just know that it's there. And if I know that I'm always raising some base called 2 to some power, all I have to maintain is the power. So if I maintain this power and I maintain that part of the number, I can easily, if the hardware will maintain this number for me when I do math operations on it, I can easily restore the number back to this and then actually multiply it out to get the original value. So this sounds like it has some promise. It sounds like there might be a little of thinking work to do to get it to happen, but that work's been done for us by the standards committee. The IEEE has developed a standard that says we're going to be able to encode this. Now, one of you should have been raising your hand going, but, what if I want to encode the number 0? I can't possibly put this 1 in there. And you're absolutely right. 0 is a special case. We'll find out that so is infinity. So is something called not a number, which can be accidentally generated by doing math that doesn't, actually produce a number answer. So in any event, let's talk about how we would build one of these things in terms of the logic behind it. So what we said is we're always going to take a normal number, and I'll just write a real simple one out for us here, 1.1, and multiply it times 2 raised to some power. This part of the number after the decimal point, these digits here, are something that is called either the mantissa or the characteristic. If you go way back in elementary school when they taught you logarithms, which I'm joking, they probably taught you that in 7th or 8th grade, you would remember that that was the body of a logarithm, was the mantissa or the characteristic. Then we also have the thing we're raised to. The thing we're raised to, we know the name of that, that's the exponent. So we need to maintain really 3 things. One is the mantissa, one is the exponent, and the other is it plus or minus? Is the whole number either a positive number or a negative number? We can't use 2's complement for this because it just wouldn't make sense to mess around with the mantissa and characteristics and maintain the simplicity in the hardware that's going to actually do the calculation. So let's think how this number may be constructed. I'll move that up a little bit so we can see it. Now, I'm going to give you the anatomy of one of these things. First thing we're going to have is a sign bit. I'll put an S there to represent it. Then we're going to have the exponent. I'm going to put 8 E's. Now we've used 9 digits. The entire thing is 32 bits long. So we're going to have 32 bits of the mantissa. I'll just draw 2 of them and say the rest of them out to the end are mantissa. The entire thing is 32 bits in length. The sign is 1 bit. The exponent 8 bits. And the mantissa or the characteristic is 23 bits. 23 plus 8 plus 1 is 32. So that's going to be the way we want to try to encode our number. Now, the encoding itself is relatively straightforward. There is one little gotcha, and that is that the exponent is in a form called excess 127. What the heck does that mean, and why did somebody ever come up with that? They must have been drinking heavily at the Wendy's or the McDonald's. Well, Shamrock Shakes, of course. The deal here is that we would like for the exponent to always be a positive number. So if I make the exponent be 127 when the value really should be 0, that means I could take and get the number 0 as an exponent when I wanted it to really be negative 127. It would be equal to 127 when I really wanted the number 0. And of course, I could add 127 to it, where it would be a positive 127 when I had added 127 to 127. The real number I would get there, of course, is going to be 256 or 255 or 254, depending on what I'm going to show you later. But this means that when we have an exponent, we're going to encode it 127 higher than it needs to be. So in my number up here, this n I'm talking about is really, I'm going to raise it to n minus 127. Okay, so let's write that top number in that form. My number is 1.1 times 2 raised to the 0 power, right? This already has 1 to the left of the decimal point, so I don't have to move the decimal point at all. So what sign is it? Is it a positive or negative number? It's positive. So we're going to encode a 0 for a positive number and a 1 for a negative number, very much like we would with something else that was maintaining signs, but that 1 bit will maintain all of the info. Now we need the exponent. The exponent is a 0. Now, intuitively, you would think you would encode 8 zeros. But what did I tell you? I said it's 127 too high. So we'll encode the 8 bits that represent the number 127. So we have the sign, we have these 8 bits. We know 128 would have that 1 on there, and they'd all be zeros. So 127 has to be all the ones to the left, to the right of that number. Now we have to code everything that's to the right of the decimal point in our original number. That's the number 1. And we have nothing else other than 0, so we'll keep coding these out until we have, I'll pretend like I put enough of them to get 23 bits here. So 1 plus 22 zeros. So let's regroup all that. 0, 0, 1, 1, 1, 1, 1, 1, 1, and then 1, 0, 0, 0, and a bunch of zeros. If I group this into sets of 4, and there'll be some more, we can write that down. We've memorized 0, 0, 1, 1 to be a 3. 1, 1, 1, 1 is an F. 1, 1, 0, 0 is a Charlie. 0, 0, 0, 0 is a 0. And then we have 4 more zeros. This number right here is the IEEE 754 floating point number that represents this value right here. Let me copy that down here. So basically the number 1.1 is equal to that. And you might go, well, that's a lot of digits. It is, but it really solves some problems in maintaining floating point arithmetic. So let's do another one. And let's see how we would do with this. Let's just pretend for a second that we want to encode the number 12. And we won't have any fractions. We'll just make it 12.0. Let's think about how we might go about doing something like that. First of all, we need to write it in binary. Why don't you write that number in binary and stick it in the chat for me? Write the number 12 just in plain old binary. Twelve is 4 plus 8, right? Yeah, you really get going there when somebody's put an answer and you start agreeing with them. Figure it out yourself, put in the answer as you figure it out. Okay, so we know it's 1100. And if you had to look that up, shame on you, because that's going to really slow you down. Okay, so that's the number 12. Now, if this is the number 12 and we want to normalize it, there's a decimal point right there right now, correct? Where do I need to move it to? I need to move it to there. How many positions did I have to move it? I moved it 1, 2, 3 positions. So let's just remember that. I'll put over here 3 positions. Now, is it positive or negative? Well, the way we know that is this number is small. It's close to 1. We want, when we're done, to make it be bigger. So in order for this to be bigger, we have to use positive powers. So we're going to need a positive power in order to be able to get a bigger number, since we've normalized it down to near 1. So now what we need to do is we need to think about how we would encode this thing. We encode the sign bit first. It's a positive number, so we encode a 0. Now the exponent is 3. We're going to add 3 to 127. Okay, If we added 3 to 127, I'll do it on the row down here. We would take the number 127 and we would add to it a 3. Okay, that looks hard to me. I mean, that's going to carry the 1, carry the 1. How about we do this instead? Instead of adding 3 to 127, doesn't that equal 128 plus 2? We know 128 is this. So isn't 128 plus 2 going to be that? I didn't have to do all that messy math? And the answer is yes. So let's take that. Take that to be our exponent. Now we need everything to the right of the decimal point. And then a bunch of zeros after that. We'll deal with the zeros as we need to. So I'm going to take this number, shrink it down so that we can come back and put spaces at the right spots, and group it in sets of 4. And of course, we need 4 more of those to have our 24 bits, and also so the whole thing is 32 bits. So what is this number in hex? It's a 4, 1, 4, 0, 0, 0, 0. One more, 0. Have to have that many. So in order to encode the number 12, we would use this encoding right here. Okay, let me give you one to do on your own. Let's say we wanted to encode the number 5 1/2. Let's make it negative 5 1/2. Work that one and put the answer in the chat. Don't cheat and copy somebody else's answer. Actually work yours before you even look at their answer. And then put whatever you got, even if it's a wrong answer. Let me see who's getting it and who's not getting it. Nothing to be gained by pretending to know what you're doing. Now, if I make one of the problems and I make an arithmetic error, you find it when you're looking at your notes. That's why you want to rework these problems, not listen to a recording. It's also one of the things you want to be really careful of. More than likely, everybody on here is on Discord. And more than likely, the people on Discord, at least the ones that don't know what's going on, are sitting on Discord talking about video games and talking about how dumb the teacher is and how hard the class is and things that aren't appropriate to learning new material. Also, you want to make sure that you're not just, on there off the topic. When you go to do that, yes, it's nice to make friends and to do things, but find some way to study with those people. I might make typos. If I do, you need to find them, correct them, and make sure your notes reflect that. Because you don't want to, on a test, on question number 102 and you got 20 minutes to finish, grab a piece of paper and try to sort out what was I doing that night. And it doesn't look right, but because it wasn't. I might make math errors either intentionally or because I make a math error. I'm a human, and I'm not using notes when I do this stuff. So I could be making math errors. If I do and I don't see them, correct your notes. Okay, I see a couple people already submitting answers. That's great. Please do that. Remember, all these things when I ask you to participate are being captured so that I can include them as part of your participation grade. Quite often around now, I get a flood of people that decide it's time to quit the class because things are hard. Mostly you need an attitude adjustment if that seems that way to you right now. I don't see anybody on my list of people that I have, and I've checked almost everybody now, that is just totally out of place here. Everybody's capable of doing this work, but you have to knuckle down and do it, because I've heard that I'm a tough teacher. And I am, because I have high expectations for you. I want to someday be able to see you in a position where you give me a big thumbs up because you realize I was part of what helped you get there. And I don't care what it is. If you're working at, the Target in Heightstown and at least you're doing a good job of it, and you're not a mess up. I had one kid many years ago, and that has like 5 or 6 minis, who was a butcher at a grocery store. And he thought maybe he wanted to be a computer scientist. And he was really good at it. He got everything done, and he got finished with it, and could have gone anywhere he wanted. But it turned out that he really liked being a butcher, and he's still doing it today. And he's making lots of money. So, you don't just do this because you were the only kid in the room that could fix the flashing 12 o'clock on your old VCR or something. You do this because this is interesting to you, because you get excited when you see ones and zeros. If you don't, computer science isn't the right place to be, because I love this stuff. I mean, I'm passionate about it. I really enjoy people that can do this well. And you should try to get that spark if you want to do this. You don't do this for money. The money will come, but you don't do this because of that. You do this because this is something that is exciting to you, and you really like to see the fact that you can encode a Unicode, surrogate pair. That's fun. Okay, so how are we doing on this? I don't see many answers, but I see a couple. I'm probably distracting you by talking, but what the heck? My birthday was yesterday, by the way. You'd be happy to know I was stung by a yellow jacket, as usual. Every year I go out and look in my yard, and the yellow jackets come after me. But that didn't matter. I'm not allergic to them, and I guess they wanted to give me a little birthday wish. Teach me to mow the lawn on my birthday, right? Okay, well, let's work this together. If you haven't submitted an answer yet, you may be stuck, or you may be, I don't know, something could be happening. Let's write down 5.5. 5, we'll write out the full nibble. Looks like that, right? A 4 and a 1. 1/2, so point, is the first digit. That's 1 over, it's 2 to the -2, so it'd be 1 over 2. And then 4 zeros just to make them all be nibbles. So we know what that is. If we were to write that down in hexadecimal, we would write 5.8. Right? That's what it is in hex. But we won't bother this time. So how many positions do I have to move the decimal point to normalize it? I need it to look like that, right? So how many positions did I move it? I moved it 1, I moved it 2. Plus or minus? Well, our net result's going to be 5. The number we're going to use here is close to 1, so it has to get bigger, so it has to be a positive 2. Okay, so let's figure out what our exponent should be. It's going to be 127 plus 2, which is equal to 129, which after what we saw last time is you take 128 plus 1, you're still going to get 129, right? So that's easier because we know 128 looks like that. And we know that 128 plus 1 is going to look like that. So let's start writing our number. It's negative, so we put a 1. We write down our exponent. And then we go pick everything to the right of the decimal point. So we need at least that much. And then we know everything else over here is going to be zeros. Let's regroup it. And a bunch of zeros. So we group it into 4s. And we extend it till we have, 8 nibbles. So it would be Charlie, 0, Bravo, 0, 0, 0, 0, 0. So this number right here, C0, B0, and 4 zeros would be the correct answer. If you got that, great. If you didn't get that, that should be a good example of seeing how to make that work. Does anybody at this point have any questions about this process? Okay, let's take and let's encode. See, I got a list of numbers here that I've used before, just because I kind of liked them. How about 123 and I don't know, 5/16. I think I like this one because I think it's on the exam actually. Maybe disguised a little bit. But think about what the process steps are. Even if you can't do the process steps, see if you can write them down as you're going along and then just kind of follow along with the numbers. We notice when we're doing this, we're not doing as much calculating as you think we would, right? You think the calculator up here, it's been sitting kind of idle for a while. Why haven't we been using it? Well, if we went to the programmer page, there's bound to be one in here for programmers, we probably could figure out how to use that to do some help us here. But on a test or something, you're going to just have your grocery store calculator at hand and able to finish in time with. So let's actually work on this. First thing we need to do is we need to take the 123 and turn it into binary. So 1, 2, 3, and this is learning something we already know, right? What's the biggest number less than or equal to 123 that we can subtract away from 123? Well, we know 1, 2, 4, 8, 16, 32, 64, 128. 128 is too big, so we must be going to take 64 away from it. Everybody agree with that? Okay, let's put 123 in the calculator and subtract 64. I'm lazy. I'm not going to type that and figure it out. So that's 59. That's grocery store stuff, right? Next biggest number, 1, 2, 4, 8, 16, 32, 64. 64 we already taken, so it has to be a 32. So subtract 32. Come over to our calculator, and minus 32 equals 27. Okay, biggest number, 32 we've already used. 16 can go away from that, right? And come over here and go minus 16. That gives us 11. Even though we know what 11 is, we'll go ahead and work it. So I can subtract 8 from that. That leaves us with a 3. I can't subtract a 4, but I can subtract a 2. I don't need the calculator for this. I can say that's a 1. Then I can subtract a 1, which will give us the 0. So we know the bits to be turned on are the 64, 32, 16, 8, 2, 1. So let's write those numbers. Okay, we don't need the 128. We need the 64. We need the 32. We need the 16. We need the 8. We don't need the 4. We need the 2. We need the 1. So in theory, we just wrote the number 123. Now, if I did the math wrong, you can fix it. But actually, pretty close, I imagine. Now, we're not done with our number at that point because we still have to deal with the 5/16. Let me copy this down again so it's closer to us. So we have to deal with the 5/16. Well, let's pretend like we were just going to write the number 5, but we were going to include it in 2 to the 4 bits. Right, 16 is 2 to the 4th. So 1, 2, 3, 4, there's 4 bits. How would I write the number 5 in there? Well, that's a nibble, isn't it? I would write 0, 1, 0, 1. So if I put those two numbers together, point, 0, 1, 0, 1, I would have my whole number that I need to work with. I'll space it out a little so it's easier to see. But here's my 123. There's 5/16. We say we have 1/4, which is 4/16, plus 1/16, which makes 5/16. So now we have the number we need to work with. This is a number we're going to process. How many positions do we have to move the decimal point in order so that the decimal point is here? Right, well, let's smoosh it together. So that was what that number looked like, smushed. And how many places did we move it? We moved it 1, 2, 3, 4, 5, 6 positions. Is that right? And we know it's going to, again, be a positive number we're moving it because 123 is much bigger than 1. So let's start writing our number. The sign is 0. The exponent is going to be a 6. Okay, so 6 plus, well, 127 plus 6 is equal to what? Equal to 133. So 128 plus 5 is equal to 133. So let's use that guy, 128. And then come back and turn on the bits that would be the 5. It would be a 4 and a 1. So this guy right here must be our exponent. Now we need the mantissa. That's everything to the right of the decimal point. And let's scrunch this down and divide it back into sets of 4. Only has 3, so we can add a 0 on it, and then there'll be some more zeros. So our number is going to be 4, 2, F, 6, A, 0, 0, 0. Okay, think about that. Think if that's the answer you were headed toward. Okay, I want to do one problem where we're to the other side of the decimal point. So let's say that we wanted to write down the number 1/2. How would we write that in binary? Well, we have zeros, point, 1/2. What do we want to do to normalize it? Well, we want it to be, so it's 0, 0, 0, 0, 1.000, right? We want to move the decimal point one position. But in this time, it's in the other direction. So we can take 127 minus 6, I'm sorry, minus 1, and that means the answer, what the number we're going to have is going to be 126, right? Well, what are we calculating here? Well, we're trying to figure out what number we need to encode. So the number we need to encode is 126. It's one less than the 127 we had. So in this case, it would be appropriate just simply to take the number 127 and subtract 1 from it. So that's going to give us the exponent we need. The sign is positive. The exponent looks like that. Now we're going to grab everything to the right of the decimal point. Well, look at that. It's all zeros. Oops. What did I just do? Is this the right number? No, I put the same thing twice. That's what it is. So all zeros to this side. So let's group them up. Put them into sets of 4. There's zeros out here. And the number would be 3, F, and then a bunch of zeros. So that number right there is the number 0.5, or 1/2. So see how nice that is? That's very, very algorithmic. And we have, a very simple way. We got a sign bit, easy to determine. We have the actual exponent that we're going to raise to get the number, and it's been inflated by 127, so we never have to deal with numbers that are below 0, because the smallest power we can use is 2 raised to the minus 126th. The highest is going to be to the minus 127. Or, I'm sorry, plus 127. But we do have some special cases. Here's the special cases. What happens if the exponent is 0? Well, let's assume we don't care what the sign is. It's anything. But if the next 8 bits are 0 and all the remaining bits are 0, we have either plus 0 or minus 0. Now, plus 0 and minus 0 compare equal by the hardware, so it doesn't matter. They're not different numbers. They are written differently and might be computed differently. You know, a problem might give you a minus 0, might give you a plus 0. But when they're compared, they're identical. The rule for having a 0, though, is the exponent is all zeros, and so is the mantissa. So there is no normalized 1 hiding away anywhere. Now, what if the exponent is all 1s? Possibly in that. So we don't care what the sign bit is, but we have all 1s. Well, if the mantissa or characteristic is all zeros, we have either plus infinity or negative infinity. Now, clearly, they are different numbers, depending on the sign bit. But if you have all 1s in the exponent, and everything on this side over here is all zeros, then you have the numbers plus infinity or negative infinity. Now, if it's all 1s, and the rest of it, it has, you know, the exponent or the mantissa has any one, or actually, let's just say not all zeros. So our exponent is all 1s, but the right side, all those other bits are not all zeros, so it's not infinity. What it is something called a not a number. Not a number is a value that is not a number, meaning you can't compare it, you can't add, subtract, multiply, divide, raise to powers, you can't do anything with it that's number-like because it is not a number. As a matter of fact, you can take the one bit pattern that is not a number and then take the identical bit pattern as not a number, and you can't compare them and have them come up equal because they're not numbers. So not a number is, in advanced math, it's something that can happen. Often in part of the solutions to trig identities that don't really go to infinity, don't tend to infinity, or the types of things where you divide by 0 and you're not really getting infinity when you do that, you're getting something that's not a number. So something that can be expressed, for example, we might get some bit pattern that won't fit inside of our range here. That clearly would be not a number and would be encoded as not a number. We have one case we didn't talk about. If we have all zeros, but the other numbers are not all zeros, we have something called a dirty zero. A dirty zero is really called a denormalized number. What that means is, do you remember how in anything that did not have zero, when we had powers that were relative to 127, we always had that plus 1 or 1 point in front of everything that was hidden? Well, in a denormalized number, that number actually is shown. So we actually encode it inside of the number. Normally, we will have pushed the number so that it's something like that, and we don't move the decimal point because there are so many zeros in front of it that that number actually has to be represented, but we don't have enough range in above 127 to reflect it. So a denormalized number is called, it's a very small number, and it's always whatever is literally, including the 1 point. The 1 point will be in here, but it'll be as part of the mantissa. It's basically going to be whatever that mantissa is, or times 2 raised to the minus 126th power. So it's a very, very small number. But you can easily recognize because its exponent is all zeros, and the remainder of the number, regardless of what the sign is, but the remainder of the number is going to be not all zeros. So if I ask you, you know, what is this number right here? Oops. told you it was encoded in IEEE 754 single precision, you would tell me that's a positive 0. If I gave you that, you'd say it was a negative 0. And I gave you that, you would tell me that's a dirty 0. That number is really actually this is, well, yeah, we're in hex. This number has something, but we know that the exponent part of it, although it's encoded as 0, 0, it's really 2 raised to the minus 126 time whatever this value is with the 1 pushed that far to the right. You saw this number right here, which had all ones in the first part, but the exponent has spilled. Let me write it in binary because it's easier to see it. But over here somewhere, there's a few bits. This would be not a number. However, if it was this, and all the other numbers are zeros, that would be either, in this case, it would be plus infinity. First number was a 1. It would be negative infinity. Okay, you should be able to do these. I mean, you're going to get to do these, have fun on these on a test, but you should practice a few of these. I did post a web page that gives further descriptions if you're the reading kind. And this has everything plus some extra stuff, describes the fractions and all of these things. Has a little more than you need to know, but I think if you work your way through and remember what we talked about, you'll have no trouble navigating this page. Notice there are other formats and other hardware can support them, but we're specifically using the one that's single precision floating point, 32 bits. Okay, everybody give me a happy face this time, if you're able to hear me. Okay, there's a couple people that might not be in the class right now, hiding out. Okay, let's move on to our next topic. Okay, let's look at this circuit again. We saw this circuit last time, and we talked a little bit about the voltage at this particular point and how we deal with it. And we said that these are proportional to each other. Now, there is a way to determine this voltage relative to ground. So if we were to give this a volt, I'm going to give it an abstract volt, just called V. We know that this particular point is at voltage plus V relative to ground. We also know that ground is 0 relative to ground. So this side of this resistor would be at 0 volts. So 0 volts at V volts. And then this would be something that's in between, which is proportional to these two resistors here. Turns out this can be computed. I don't believe I gave you the formula last time, but this, and these are called nodes. The area between components are called nodes. This node's voltage, which basically is going to be a voltage divider. We're dividing the voltage V into two parts. The part that's dropped across this resistor and the part that's dropped across this resistor can be expressed by the node voltage. I'll just call it V sub n. Is going to be equal to the total voltage in the system that we're concerned with, or being dropped across the resistors, times the bottom resistor of the pair over the sum of the two resistances. And we'll see this formula come up in other ways later. But the idea here is that if we sum these two resistors together, basically we're replacing them with the equivalent of a single resistor, right? That would have been replaced with a single resistor that has a total value. That's this. And if R2 is taking some proportion of that, we put it over the top, that'll fractionally tell us of the total how much is attributed to R2. that proportion can then be multiplied times the voltage dropping across both of them to tell us how much voltage was dropped right here. So this formula comes in handy if we have a proportion. So let's say we have 9 volts over here. I think we did this actual problem. And we said this was 100 ohms. And this guy over here was 200 ohms. Well, we can work the problem over here if we look at the entire thing. We say in this case, we're going to take 9 volts. We're going to multiply it times 2, which is the 200 ohms. This is volts. Divided by 200 plus 100, which is 300 ohms. And what we'll see is that if you get rid of the zeros, we have 2/3 of 9 volts. So 2/3 times the 9 volts. Well, we're real quick in our head, we can see that 1/3 of 9 is 3 volts, right? So 2/3 is 6 volts. So we would expect to see 6 volts here if we put a meter on it, measured from here to here. That means this resistor is responsible for dropping 6 volts of the total voltage. The other resistor must be dropping the remaining 3 volts. So now if we wanted to find out what the current is, we could do one of two things. Either we could take and first of all add them up. So we could work the circuit this way. We could say we have a 9-volt battery going through a single resistor back to ground, where this is 9 volts, and this is the total voltage, or not it, our total resistance, which would be 1 plus 2, which is 300 ohms. Or we could take and we could just work the problem across the first resistor. We could say that our current, again, we're solving for a current that goes through the entire circuit. We could just make the assumption that we only have the top resistor value here, but the battery in this case would appear to this resistor as though it's only 3 volts. So we could say we have 3 volts dropping across the 100 ohms here. And we could do the computation. Here's our current. Or we could take the other way. We have 3 ways even to check our own work here if we wanted to. We could say we know we have another resistor that we could be checking, which is this guy. And from his perspective, he sees a 6-volt battery. He's solving for a particular current. And his value is 200 ohms. So we could take any of those we wanted to. Let's take the 6 volts and divide it by 200 ohms. We would see we had 30 milliamps. Now, how did I get that calculator value to that? Well, in order for us to be an engineering form with, significance, we had this number here, 0.03, which we know there's another 0 here. We always want to move the decimal point such that 1, 2, or 3 of our significant digits, and here's our first significant digit there, is to the left of our decimal point. So we could move it not 1, we could move it 2, but we need it to be a multiple of 3. So we're going to move it 3 places. And since we moved it 3 places in the make it smaller direction, we could go back to our web page. Whoops. We could go to our prefixes, which we've memorized the first few of. We could say, well, 3 is milli in the negative direction. So when I write the number down, I would write the 30 milliamps. So the current here is 30 milliamps running through this. We solve any of the others, we'll see it's also 30 milliamps. Because these are in series, the same current passes through everything. We can solve using both resistors added up. We can solve using just this one with its contributed voltage drop, or this one with this voltage drop, whichever is the easier to use. So we go to our box, our Radio Shack, and we say, I want to find a 100 ohm resistor. What's the color code for a 100 ohm resistor? Well, 1 is brown. 0 is black. I'll put BK for black. We added 1 extra 0. 1 is brown. And since we didn't specify anything having to do with the tolerance, we'll just pretend like it's a 20% resistor. So there is no fourth band. However, if it's a 20% resistor, that means it could be as low as 80 ohms, and it could be as high as 120 ohms. Let me make this a little bit bigger. So if we were interested in what the values of those would be, and we will be later, we could see that this is going to allow a lot more current than the 100 would, and this is going to allow a lot less. So depending on whether the 30 milliamps is enough or too much, we might make other decisions about the tolerance. But in any event, we should go check and make sure 100 is available. To do that, again, we go to the website, or we remember, and we look at the standard resistor values, and we see that 10 is available as a 10% and as a 5%. And I'll also tell you, even though it does, we don't show it because we really in life would never use a 20% for this type of circuit. It is available there as well. How much wattage would we be burning? How much would the resistor be using up if we were to have it at its minimum maximum value? Well, we'd have to do the resistors independently. We can't do it on this and get any meaningful data for this purposes. So what we would have, well, we could here, we couldn't do it on the 300. So we have to work the power problem twice. First of all, if this were 80 ohms and it's dropping 3 volts, we would take the 3 volts, we would divide it by the 80 ohms, and we'd see here that we have 38 milliamps. That's a lot more than we had. But now we want power, so we're going to take the current and multiply it times back the 3. This is 113 milliamps. The 3 types of power resistors we have are 125 milliamps. I'm sorry, milliwatts. This was watts, by the way, milliwatts. Milliwatts, 250 milliwatts, and 500 milliwatts. Where this is 1/8 of a watt, this is 1/4 watt, this is 1/2 watt. Remember, you can't tell the wattage other than knowing it's the right one or the package label says it or you have experience. This number is way, way too close to 125 for my tastes. So I would buy a 1/4 watt resistor. So we've said here we would be getting a 100 ohm 1/4 watt 20% resistor, where we've determined that the color code is brown, black, brown, and a no fourth band. We also probably would want to go check this resistor with the same type of calculations. What's the worst it could be? Well, it could be 40 worse, so it could be 160 all the way up to 240. The low number matters because it's going to be with the most current. We're checking for heat, right, with wattage. But we also care if this were 240, would the number 30 milliamps have dropped so much that it couldn't efficiently do the work we need it to do? It doesn't make as much sense here because we're not showing any work being done, but it will soon. Okay, a couple other quick diagrams I want to show you, but not necessarily talk about tonight. First one is this guy. Actually, I'll show you him in Paint. He has 2 resistors in parallel, not in series. So the issue here is that the current that's coming into the circuit from the battery this direction has to go into this node and then split, and part of it go this way and part of it go this way. Then when it gets to this node, rejoin, and these two have equal value. How do they split? Well, they split proportionally to the values of these two resistors. These resistors are equal, we'll get half the current through each leg. This is called Kirchhoff's current law, which says when you have current going into a node, the amount that went in has to come out. So that goes into has to match the current comes out of. So if I had 10 going in and 5 here, 10 would ultimately come out here. Voltage around this loop is raised some amount and then redropped. It would happen inside this smaller little circle here, but I'm going to save the definition of that for that later. But also the bigger loop would, whatever it was raised to by the battery, it would have to be redropped to get back to the zero relative to ground here. We'll talk about this in more detail. I just wanted you to see that. I also wanted you to see this guy, I believe it is, because as you're reading about this stuff, you can intuit the rest of it without me having to cover it in class. This one not only has these two in parallel, but it also has this one, which is controlling it. So we could think of this as being series with those two in parallel. So we could actually kind of redraw this circuit with a battery going into a resistor, going into another resistor, where the value of this resistor here is really the value of these two combined in parallel. The formula for finding the parallel resistance, let's say I wanted the resistance of R2 and R3, so R2 in parallel with R3, is equal to R2 times R3 divided by R2 plus R3. And obviously, once we have them in series like this, we know how to work this problem because we could then combine them to be a single value. And we can figure out what all the resistances and voltage drops and things are in a very complicated circuit. But I'm not going to push us on that right now. We have some different type of work to work on, which will involve knowing this later. So as you're reading about it, read a little bit about how you find parallel resistors. You'll also find that if there's more than two, the total resistance in parallel becomes a little more complicated. It becomes 1 over R1 plus 1 over R2 plus 1 over R3, because you might have more than two in parallel, and so forth, dot, dot, dot. If you just took the 1 over 2 case and refactored it, you would actually get this formula. But this is the general formula for resistors in parallel. So to combine these into a single resistance value, so you could determine what the total current in the circuit was. Okay, let me close those down. Before I do, does anybody have any questions? Okay, give me a affirm if you're still able to hear me. Yeah, let's see if I got anything open here that I didn't want to open right now. No, good, okay. Okay, so let's think about another circuit component that we might encounter along in our travels. This circuit component is called a diode. Oops, need a pen here. I need to be fat-fingered, I still am, okay. A diode looks like this. A diode is a semiconductor. I'm not going to write that out. Semiconductor, S-E-M-I, conductor. And a semiconductor is made out of either silicon or germanium, not geraniums, but germanium, where modern ones today, the ones you'll encounter, are made out of silicon. Silicon, the element, not silicone like body parts are made out of, but silicon. Silicon is a very stable semiconductor where it is not really good at conducting, nor is it good at insulating. It's kind of halfway between. But if you take it and you add certain elements to it, you're able to turn it into something that has extra electrons or has extra places for electrons to go, which we would call conventional current elements. We call those two materials either P material or N material. N material negative has too many electrons for the chemical element as silicon, so it has a bunch floating around in it. The P material has a bunch of holes, which are just kind of waiting for electrons to fall into it. We often call these, when they're pushed together, a p-n junction. A diode is an example of a p-n junction. The arrow part is the P part. The line part is the N part. So this is the negative end. This is the positive end. Conventional current wants to flow in the direction the arrow points. The positive material is called the anode. Which is the plus end of the diode. And the other end is called the cathode. We used these words already earlier with the batteries. However, a battery uses them to mean exactly opposite. In a battery, the anode is negative and the cathode is positive. In the devices that drop voltage, the anode is positive and the cathode is negative. So most of the time we use this definition. This is the case. The line is the cathode, the arrow is the anode, and current wants to flow that direction. As a matter of fact, it does not and is heavily resisted in flowing that way. I put some little can't go marks on that. Now, what does that really mean in terms of if we were to draw kind of a graph representing it? Well, in general, if we use a Cartesian coordinate system here to represent things, we're going to have the x-axis represent the applied voltage. And if it's applied in a correct way, meaning so that the current wants to flow, we're going to graph it on this side. If it's put in the opposite direction, so current doesn't want to flow, we're going to put it on that side and call it negative biased. Negative biased, positive biased. A diode, normally if we start applying voltage, and we're going to think of this as current. The vertical axis is how much current is flowing, either in the correct direction or in the wrong direction. So an ideal diode would immediately allow us to apply any amount of voltage and the current would increase phenomenally. And it would also block any in the other direction, so it would always remain zero. In real life, though, as we start to apply voltage, very little happens until we get to about here. Then it starts going up, not vertically, but close to vertically. This point right here where it starts to do something interesting is kind of its turn-on point. For a diode, or for a silicon diode, it's at 700 millivolts. We're going to call it, though, 0.7. I told you earlier in the semester there were one or two places where we don't put it in engineering notation. This is to please the engineers because they call it 0.7 volts. But at roughly when we supply 0.7 volts, if we continue to apply voltage, it'll increase the current much faster than it can possibly increase the voltage. So we would get almost what we would consider very forward bias. Basically, the diode goes away. It has 0.7 volts dropping across it, but any amount of current we give it, it can pass it. With the caveat that at some point the voltage will be so much that, let's draw a little sparkler up here, it'll blow up. So we have to make sure we're controlling the amount of current we let it flow. But as long as it's below the blow up point and it's above zero, it's going in the forward direction. It's the way a diode is supposed to work. Now, let's assume we apply it in a negative direction. It will block it for quite a while to what's called the avalanche voltage, at which point it'll start dropping rapidly. Now, there are some diodes, in particular something called a Zener or a Zener diode, for which that reverse operation allows us to build voltage regulators. However, for most diodes, this voltage is a spot where you don't want things to happen because it's going to very shortly reach sparkler status in this direction. Once it reaches sparkler status, it's gone. You have to replace the diode. It's no good any longer. So we could create a circuit where we would have a diode in it, and we could do a quick calculation to see how that might work. So I'm going to erase this, and I'm going to draw us a quick circuit containing a diode. First of all, we need a battery and a resistor to be able to limit the amount of current flowing in the circuit. We already know if we hit sparkler status, it's no good. We then need a diode. Since this is the positive end of the battery, we hook the anode of the diode to it. Then the cathode is going to be hooked to the bottom side of the battery, which is our reference point that we call ground. Now, as long as this battery is higher than 0.7 volts, current will flow through this diode. If it's less, there will be a little, but it's be tiny, and we call it leakage current. So let's assume we'll put a pretty healthy dose to it. Let's give this 5 volts. We know this to be the plus end of the battery and this to be the negative end. So current is going to flow through the circuit in this direction. If we reverse the battery or the diode, assuming the current was limited enough by this, we wouldn't have any current flowing. It would simply be 0. We could use that, for example, if we had a sine wave and the sine wave were under some controlled conditions, we could put a diode in the circuit such that we only got the positive humps. We'd block all the negative humps. And we would use that in a voltage regulator to make sure that whatever the hump is the voltage we're trying to get, and that we're definitely not getting any negative voltages. And then we'd hook in some capacitors and other things to ensure that that never exceeded the voltage we needed, nor the currents we were trying to get. So over here, how do we analyze this circuit? We have 2 devices. This does not act like a resistor, but we do know one thing about it, and it does have a name. We'll call it D1. It's the first diode in the circuit. We'll call this R1. It's the first resistor. We'll call this the first voltage source, V1. We know that there's going to be a drop across the diode if it's actually operating, and it's going to consist of 0.7 volts. How much voltage will drop across the resistor? Well, 5 minus 0.7 would be 4.3 volts. Now we should be able, we have a voltage drop. We have a current flow, and we have a resistance. If we're given either the current flow we want or the resistance we have, we can compute what the value of the other one has to be. So let's assume for a second that we took and we knew what the current we wanted was. We want to have 20 milliamps. We'll call that current I1. Well, that says that the diode is going to also have 20 milliamps flowing through it. So we look at its data sheet and make sure that it can handle 20 milliamps, and it can. So we can now consider here what value resistor we need. To do that, we take Ohm's law. Ohm's law says that if we take the voltage, which is 4.3 volts, and we divide it by the current we want, which is 0.02, it's 20 milliamps, right? We'll find out we can get a 215 ohm resistor. And we can make our circuit operate exactly like we needed it to. Okay, now, let's assume we went to the store and we looked at values of resistors that are available. We see there are only 2 digits, they're not 3 digits. So what's close to 215? Well, 220 is pretty close. We also could get a 200. If we got 200, we'd have to get 5%. But we get 220 with either 5 or 10. Let's assume for a second that we're going to get 220 ohms here at 10%. So we're going to get a 220 ohm, not a 215 ohm. And we said 10%. So the actual value of this resistor is going to be 220 plus 22, or 220 minus 22. So that means this actually could be a value of 242 ohms. Or it could be all the way down at, what's that, 198 ohms. So what we would need to do is we would need to check both of these values. First of all, check the smallest one, because that'll give us the most current, if you think about how Ohm's law is formed. Check this one to make sure that we don't have so much current that we would burn up the diode. We also have to check that, because this will give us a lower current, that at 242 ohms, that we have sufficient current to run the circuit for whatever we need to do. So we could do those calculations. I'm not going to do it on this problem, but we could. We also then, when we're done, would take this value and do a wattage check. We check the power, because that's the most current we could produce, to make sure that the size of the resistor we've gotten. We know it's 220 at 10%, but what we don't know is it an 1/8 of a watt, a 1/2 watt, or a 1/4 watt resistor? So those calculations remain undone on this particular problem. So let's amp up our work here a little bit, and let's say that what we wanted to do was we wanted to actually use a different type of diode. Am I erasing anything? I think I ran out of my erasability. So let's just do it from scratch. That's even easier. You might as well see it from scratch. Okay, before I start on this, does anybody have any questions about what we just did? Okay, if I take a diode, and I have it fabricated in such a way that the light in it is in a human seeing or infrared band where it's useful, I can create something called a light emitting diode, an LED, which you've all heard of. Probably have a bunch of them in your car on the dashboard. We sometimes draw some little arrows from this or other marks to indicate that it has light coming out of it. We normally will name it like LED1 instead of D1. But other than that, it pretty much matches the characteristics of a diode, regular diode, except when we had this chart, do you remember this? It goes further over before it starts to go up. It blows up a little sooner. And in the other direction, if it's reversed by it, it blows up very soon. So it has to be handled with a little more care. But again, this is the anode, that's the cathode. Current would flow this way. And if current is flowing above a certain amount, light is seen. If it's too much, burns up, never shows light again. Or if it's put in backwards and the voltage is high, it will often get burned up as well. Now, in a particular problem, for example, if I don't give you some design requirements, let's have our first set of requirements. The first requirement is that if I don't tell you otherwise, this point right here where the LED turns on is at 2.1 volts. We call that VF, V forward. It's the forward voltage across the diode when it's reached the point where it's turning on. We also are going to go to the spec sheet, and if I don't tell you otherwise, your diode needs to be using 15 milliamps of current to be seen and should not have more than 25 milliamps passing through it to keep from burning up. So it has to be in a range from 15 is safe, 25 is safe, above and below that is not. So if I were going to design for this, I would pick some other value. I wouldn't pick 15, I wouldn't pick 25. Put in chat the value you think you'd use to design with, knowing that as the current range. What current would you plan for through your LED to avoid being too dim or burned up? Put the value in milliamps you think you would design using. Okay. You guys either talk to the people who were in class last night who got it wrong, or you guys are smart. And we'll go with smart for now till you prove otherwise. I would pick a number halfway between. Halfway between means I would normally design using 20 milliamps as my assumed current, because I know the resistor that I use will probably not really be the value I compute. And I have to have some tolerance above and below in order to avoid problems. So you want to write these down for sure as things that if I don't give you a problem, now I might give you a problem and say that the forward voltage across the LED is 1.8 volts. In which case, these stay the same, but that changes. Or I might say, oh, this is a bright LED. You can use it anywhere from 25 milliamps, up to 30 milliamps. So given that, write in chat what value you would probably use. Yeah, 27.5 milliamps. That would be a really hard one to design for, because unless your resistor was very precise, it's going to be easy to go over or under. Remember, of course, your LED, the resistor is limiting the current, but you can only use the ones that exist. So even though you find you can get everything perfect with 123, ohm 5% resistor, there ain't no such thing as a 123 ohm resistor. There is, but they're not in the ones you're allowed to pick from. They're too expensive. So this is how we would do this. Now the circuit looks the same pretty much. Let me grab a copy of a LED circuit. Actually, before we do that, let me grab here's an LED. It's on its side. Could be pointing up. It's not. So this is the part that the illumination comes out of. It might be frosted. It might not. You might be able to see the elements inside. There's a band around the base of it. The band doesn't go all the way. There's one side that is chopped off flat. The other side has a band all the way up to that point. So there's one little chunk cut out on this side. Now notice, if you have not cut the leads off, the shorter lead is the cathode. The longer lead is the anode. This is the plus end must be pointed toward the plus side of the battery. This must be pointed toward the negative side of a battery. But once you chop the leads off, you can't tell that anymore. We know if we plug it in backwards, it may burn it up. So instead, look at the edge. If that flat side is there, that is the negative lead that's closest to the flat edge. So this is how you would take a diode and in a picture, and I might show you a picture of a circuit and ask you, is the diode in correctly? You could look and study the picture and notice that the flat edge is perhaps on the wrong side, and you would go, no, it's not. Don't turn that circuit on. Okay, so let's work with the circuit. This guy can go into hibernation for the moment. I believe it's this one. Okay, looks familiar, doesn't it? Looks like the diode circuit we drew a couple minutes ago. The only difference in this one is we have replaced the diode with an LED. Only thing is this funny little line, and we changed the name from D1 to LED1. Everything else is the same. So you'd expect that the circuit problems are going to be fairly much the same to work. And indeed they will be. So let me make this small enough that we can see it and give me some writing room over here. Okay, normally if we were in a hands-on class, we would be building this in a lab. I would, out of my stash, I would give you some LEDs to work with, a bunch of resistors of the correct values and some wrong values. And then we would use the Arduino to supply this power so that we could actually, see if we could get the LEDs to light up under particular circumstances. And I have, I buy the parts by the thousand. And so I have enough that the entire class could have one of a red, one of a blue, one of a green, one of a white. And I would just basically give them to you because I pay pennies for them. If you went out and bought them, they would be expensive. So that's why I didn't ask you to buy a kit with all these in them. We may talk later in the semester about, for those of you that really would like to build some of this stuff, I'm trying to look and see if there's some way that we can get a small enough kit that doesn't have inappropriate parts. But usually the problem is that when you compute the resistors, you wind up not having the ones you need in the kit. So let's work this on as though we're just doing a circuit diagram, but we can imagine when we say it illuminated, you can go, oh, how beautiful. Okay, so what we need to do is we need to take and we need to determine some things. For instance, we're designing the circuit. So if I'm saying we're designing it, I can't give you a resistor value and know for sure we're going to be successful because the resistor value might not allow the forward voltage to fall in the correct range. And I might give you a problem like that sometime, and that would be part of the solution would be, I have to get a different LED with different forward voltage characteristics because I can't design one given that value. But I can give you different voltages here, and I can give you specs for this or not. If I don't give you specs, we make some assumptions. What are the assumptions we make about an LED? What is the drop across it? Well, first of all, we need to check to make sure it's in the circuit in the correct direction. Is it correct direction? And the answer is yes. The plus end is hooked to the plus end of the battery. The negative end is hooked to the negative end of the battery. What voltage drop are we going to have across the LED? So we would give it a name of VF or VLED1F. I just put VF because we know it's the forward voltage. What would that be? Put it in chat. Okay, we know this is not a regular diode, and remember I drew you a different picture for an LED. I said it doesn't start happening until V forward, which is at 2.1 volts. So you make the assumption when you're working with LEDs, instead of 0.7, you make 2.1 volt be that forward voltage. Now that means the battery has to minimally be 2 point something higher than 2.1 for the LED to be on. But we also know that we have to have a current passing through the LED of at least of at least 15 milliamps and no more than 25 milliamps. So we determined that we would design this making the assumption we had 20 milliamps flowing. Okay, we still can't build this because we have still some unknowns. We don't know, this guy we got plenty of stuff for. We know he'll work, if 20 milliamps go through and it's at 2.1 volts, we know he's going to be on. We can't compute the resistor because we're missing two things. We're missing the drop across the resistor, which is whatever's left over after we've taken 2.1 away from whatever the battery power is. And we're missing the resistor value, which we're probably going to compute because it's probably more likely I'll give you this. But I might give you this and let you figure out what battery you needed. So let's say in this case, we're working with a 3.3 volt battery. How much is going to drop across R1? Well, R1's voltage drop which is its forward voltage, in its case, it's just its voltage or voltage drop, is going to be 3.3 volts minus something. Put the answer in chat. What's the answer going to be? Well, what's the something? The something we're going to take away from it is the 2.1 volts. So we can do this on the calculator if we don't want to do it by hand. Whoops, I've got to hit a key here that's correct somewhere. 3.3 volts minus 2.1 volts equals 1.2 volts. That means that our resistor has available to it 1.2 volts. So now we know a voltage, we know a current, we should be able to compute the resistance. V is equal to IR, so voltage, 1.2 volts, divided by the 20 milliamps, or 0.02 amps, should equal the resistor value. So let's try that. We have 1.2 volts. We're going to divide it by 0.02 amps. That's our 20 milliamps. That's going to give us 60 ohms. So 60 ohms. Okay, so if we did that, we would have 20 milliamps, our LED would be on, it would have 2.1, we would drop 1.2. Battery, everybody would be smiling. Let's draw a big smiley face over here. And everything would work. But then we realize, what if we go to Radio Shack and can't get a 60 ohm resistor? So let's see if we can. We have a 68 and we have a 56. We have a 68, we have a 62. And what did we need? 60? That 62 sounds pretty close. 56 is further away than 62. So let's get a 62 ohm resistor. So we have 62 ohms. And we saw that had to be at 5%. Wasn't available at 10%. Okay, so with 62 ohms, what's the color code we need for that? Six is blue, 2 is red. So blue, red, what's the color of the next band? Drop it into chat. How many zeros are there after the 62? There's none. What color is 0? It's black. I'll just put B, okay. And at 5%, that means the next band is golden. So 62, let's find out what 5% of 62 is. 62 times 0.05 equal to 3.1. That doesn't sound like we're going to have too much problem adding those up. So 62 plus 3.1 and 62 minus 3.1. Okay, so add to 62 plus 62. It equals 65.1. Remember, this is ohms. That's the maximum value it can be. And then we can also take 62 and subtract 3.1. That's going to be 58.9. Okay, so let's build our little, oh, we can put our table off to the side here. So if it's 65.1, that's more resistance than this, so there'll be less current here. What we do need to do, though, is calculate whether or not we have the minimum, which is 15 milliamps, available to us. So to do that, we need to take the 1.2 volts that's dropping across us, 1.2, and divide it by the 65.1, which will give us our voltage. I'm sorry, will give us our current, and then multiply that back times 1.2 so we get power. So we'll get two numbers as we go along. So what do we need? We need 65.1. Actually, we should do it the other way. We should take the voltage, which is 1.2 volts. We should divide that by 65.1. That means our current here is going to be 18 milliamps. Is 18 bigger than 15? Yes. So we know we're safe if it's that value. Now that value times the 1.2 gives us the power dissipation, which is 22 milliwatts. So it's perfectly okay for this resistor, at least for the tight end, to have been 1/8 of a watt. But remember, we don't care about that. We care about when it has the most current, which is here. But we saw that this is going to have 18 roughly milliamps as a minimum. That's enough to turn the light on. So let's do the other calculation. 1.2 divided by 58.9. It's going to be 20 milliamps. That's definitely less than 25. So it could be as high as 20 milliamps. So far, we're seeing really good stuff. So what we need to do is check the wattage here, because this is the higher number. Multiply this times the 1.2 to get our power in watts, and we come up with 24 milliwatts. 24 milliwatts is way lower than 1/8, so it's going to be safe for us to buy that resistor as an 1/8 watt resistor. So we're going to go to the store. We're going to ask for a 62 ohm, 5%, 1/8 watt resistor, color code of blue, red, black, and gold, and walk home with that and insert it into our circuit right here. Put our LED here and a 3.3 volt battery there. This will light up. There's no question about it. It's not going to be like it maybe won't, maybe will. This will work, unless you previously burned out the LED by putting it in backwards. Anybody have any questions about what we just did? Okay, I'm going to ditch that for a second and come back to it. Wish I was closer to that machine. Okay, here's a problem you might get on an exam. Given a 9-volt battery here and an LED which needs to have a current based on the standard value the class uses for a standard value. This is what I would be. But different than the class, has a 1.8 volt drop as its forward voltage. It's a green LED. And it's typically the things. What I want to know, let me do this for the moment. What I want to know is what value resistor do I need to buy, color code for it, and whether or not it's going to be safe to put in the circuit. I'd like you to take about 5 minutes and work that problem. And once you have the answer, simply put in chat the fact that you have the answer. Don't put the answer there. Just put the fact you have the answer. So enjoy. I'm going to sip my coffee, which I think I made yesterday morning, judging from its taste. Now, if you are having trouble working on the problem and you do need to use Discord to talk to one of your partners, this would be a great time to talk, because I didn't disavow that. I didn't say you couldn't work with somebody on this problem. If you wanted to use the chat that's on this, you could use the chat. If you wanted to use some out of band, type of something else, some other way you need to talk to somebody, it's okay. But see how far you can get with this. Don't just, sit in your chair and twiddle your thumbs. We want to make sure that we have picked a resistor which is safe for this circuit, and we want to know, what we would ask for and how we could check with color codes and things by buying it at a store. So by all means, figure out how, don't just sit in your chair or don't go to the kitchen. Now's the wrong time. You can go to the kitchen later and get yourself something to snack on. We don't have that much more class time tonight anyway. So see if you can get this done. And don't use any, calculators or anything that are fancier than what we've been doing in class. Do them the way I do them. That will definitely help you in the long run. I mean, admittedly, you could just use a circuit simulator and come up with the answer, but that's the wrong way to work the problem. I have fired many people that did that. Now here's a perfect example of we're taking good notes. Instead of writing down exactly the formula, instead of saying, calculate the current next, what's the drop of the voltage on the LED? What is the next component we do? Instead of specifying what's going on, you may get too many hows in there. You may just have a whole series of formulas now and you have no idea what those numbers came from. So it's better to know what we're doing as we do each step. And that'll really come into play as we start to take some of these simple things. I don't want to scare you, but we really amp up in a couple sessions and really start moving quickly through the material. Right now, we're getting an alphabet, a set of words, some skills to work with. But once we get into the meat of the course, we have to move in order to cover enough things in this class. And again, this isn't the time to drop out of the class. This is the time to get your attitude set so that you know you're going to do well and you're going to prove to me that you can do it and prove to yourself. I would like nothing better than to give all A's. One of the reasons is because if you give all A's, you got to go to the president of the college and explain why. And I love talking to her. She has no idea what I'm talking about half the time because I'm talking about technical things, but she's a good president in those senses. She will listen to me. Okay, take another minute and a half and our 5 minutes will be up. And if you're already done, check your answers. Make sure you're not, oh, I missed that, and then everything from that point on is wrong. Okay, you should have some answers. Yeah, a couple people said they have an answer. Good. I'm not going to ask you to tell me what it was because otherwise everybody's just going to copy it and type it in also. But let's think about the problem. We have 1.8 volts dropping here. We have a total of 9 volts in the system. That means one of the first things we need to do is compute how much voltage is dropping across the resistor. Let me see if I can make this window so that it's big and calculatable at the same time. So if I take 9 volts and subtract the 1.8, I get 7.2 volts. So let's assume that's right. That's the number now we're going to be working with the Ohm's law portion of this part of the circuit, because it's relative to what is resistance here and current here is relative to the voltage drop across it. Now, because we know that, and we know the current we want to be working with, because we haven't been told otherwise, we know 15 is too low, 25 is too high, 20 was just right. The 20 milliamps would be flowing here. So to get our resistor, we can take the 7.2 and divide it by 0.02. That's going to give us a 360 ohm resistor. Okay, now we don't know for sure if we can get one of those or not. So we'll use our page of standard resistor values. What was the number? I already forgotten. It's 360. Here's one. None here. So it looks like if we get a 5%, we'll be okay with 360. So let's put at 5%. Let's multiply 360 times 0.05. So we have to add and subtract 18. So it's going to be plus and minus 18. So what's that mean? That means it would be as high as 378 and 360. I can't do the subtraction in my head here with this pencil in my. So 360 minus 18 would be 342. Okay, while we're here, what would the color code of a 360 ohm resistor be? Three is orange, blue. So we have orange and blue, orange. I'll put BLU. We have 1, 0, so that's brown. Put BR for brown. And it was gold because we said 5%. So we know most of the stuff we need to know about that, except we don't know what power it's going to need. But we do need with these numbers now to calculate that we have sufficient current going through the system. So let me clear this, and let's say we wanted to have 7.2 volts divided by 378. That's going to be 19 milliamps. Is 19 between 15 and 25? Well, it is indeed. So 19 milliamps sounds good. Let's do the other one then. Let's take 7.2, divide it by 342. We get 21 milliamps, okay? That sounds safe. It's in the Goldilocks zone there. Now, because that's the smaller resistor, that's the highest current, we need to take this number and multiply it times the voltage to get our power. So times 7.2 equals 151. Well, 151 is certainly bigger than an eighth of a watt, which would be 125, but it's sufficiently less than 250 milliwatts. So it's safe for us to buy this thing as a quarter watt resistor. So it's going to be a 360 ohm resistor, 1/4 watt at 5%, and we're going to know the color code to check it is orange, blue, brown, gold. Now, anybody following along, did I make any typos? Were my calculations correct? Like I said, I don't use notes on these, so I could make the same mistakes you're using or making. Okay, we'll definitely be doing some more of these, but we're also going to be shortly introducing a transistor into the mix. And a transistor is going to be more than just one path in and one path out. There's going to be two paths in and one path out. And the circuit we're going to do, I have any on the, yeah, I probably have one here that we can look at without me posting it.
Sorry, Professor, I have a question.
Okay, just 1 second here. This is the next circuit we're going to be working with beyond, which is it has a transistor in the middle. We have two batteries, two resistors, and an LED. So that you don't fall too much in love with that, I'll get rid of it. Who had the question?
Never mind, it was answered in chat.
Okay. I should actually read your all's chat sometime. You might be saying that I'm the worst teacher you ever had. I'd hate to see that, but it could be happening. I've had people that really didn't like me. One of the really stories like that is I had a student who absolutely despised and hated this class. And so they were going to provide with me with as much grief as possible, and they were going to try to ace the course. They aced the course. Unfortunately, I didn't really catch on to the grief thing until the end, so I didn't know I was supposed to be grieving. But they did extremely well. Years later, we're talking 10 to 12 years later, I received an email from them, and they were working for one of the big software companies in the United States, and they wanted to thank me for the class they'd taken, because they said it was the hardest computer science class they'd had, including their master's and doctor's thesis that they had done, and that what they had learned had been so helpful because it was all practical stuff. Everything they had, they really needed to do. There wasn't highfalutin, we'll talk about it, but if you plug it in, it's not going to work. So keep that in mind. You may be in 20 years wanting to send me, boy, I'll be really old then, but you may be wanting to send me an email for the fact that you were really, really successful, and you were successful in my class, and you proved to me you were going to be. So be that guy or that gal, you know, be the person that really can show me you can do this stuff. I know it is tedious and it's complex and there's lots of numbers and there's lots of stuff, but do the best you can. Really see if you're going to be the person that wants to do this. If you're not, you'll learn it. If you are, be the one that can really do it well. Don't be just kind of one of the people that passes through. Okay, I believe it's 20 after. If anybody else has questions, let's field those real quick. Today's, what day of the week is today? Today, Wednesday. So I guess our next class is Monday. Am I right? Give me a green light if I'm right. Okay, well, at least we'll all be back on Monday then. So I'll see you guys then. Have a nice weekend, and hopefully you can do some studying on this material. We can't have office hours on Friday this week because the school's shutting down the computer during the time I would normally have them. But soon I'll make some extra time outside of class available to you. Okay, good night, and you guys throw your microphone on, say good night, and I'll talk to you or see you in class on Monday.
How about
Good night, Professor.
good night, Professor?
Good night.